Hello to everyone watching on YouTube. We have an empty classroom today, so I'll just be recording this and putting it up on YouTube and putting it up on the class website. Today, I'm going to expand on the topic we talked about yesterday, or we ended with yesterday. So we're looking at systems of linear first-order equations. And I'm going to start off by just working a few examples. So here's the first example. X prime equals 3, 2, minus 2, minus 2, x. And so as we saw before, there's a procedure for solving problems like this. The first thing we want to do is find the eigenvalue, eigenvector pairs of the matrix. Equivalently, what we're doing is we're finding the characteristic polynomial of the matrix and finding its roots. And what we've seen so far is that we can completely solve this problem so long as the roots are distinct. So we don't have any repeated roots, and also the roots are real, so we don't have any complex roots. These are situations that we'll look at maybe later in this lecture or possibly in the next couple lectures. So another name for this eigenvalue, eigenvector pair, sometimes they're just called eigenpairs. And these eigenvalue, eigenvector pairs will give us the components of our solution to this equation. So let's do that first. Let's find the eigenvalue, eigenvector pairs. So what we're looking for is the determinant, the values of R that make the determinant of this matrix equal to 0. And so the determinant of this matrix is 3 minus R times minus 2 minus R minus negative 2 times 2. So that's just plus 4. If I work out what this quadratic will end up being, we get R squared, let's see, minus 3R plus 2R minus R, and then minus 6 plus 4, so that should be minus 2. Of course, if I make any mistakes in working out these problems, this would be an exercise for you to fix these. So this can be factored pretty easily as R minus 2, R plus 1. Of course, we can always find the roots of a quadratic. We have the quadratic formula for finding the roots of any quadratic. So that's no problem if it's not an easy quadratic to factor. And what we get are the roots -1 and 2. So if we look at the eigenvectors that we get for each of these eigenvalues, we'll start with R equals -1. So the corresponding matrix that we get is 2 minus 2, 2, sorry, 3 minus negative 1. That's 4 minus 2, 2, negative 2 plus 1. Negative 1. So finding the vectors that we can multiply this by this matrix to get 0, we get, well, either of these, either of the corresponding equations will give us the conditions that we need for A1 and A2. So 2A1 minus A2 is equal to 0, for example. And we get 2A1 equals A2. And we can make an arbitrary choice for one of these, and the other one is determined by it. So the choice I'm going to make is A1 is 1, and A2 is 2. So this is A eigenvalue corresponding, sorry, an eigenvector corresponding to the eigenvalue negative 1. Now let's do R is equal to 2. In this case, we get 3 minus 2, that's 1, minus 2, 2, and then negative 2 minus 2, that's negative 4. And again, you see that one row is a multiple of the other. So what we get, if I write all this out, A1 minus 2A2 is equal to 0. 2A1 minus 4A2 is equal to 0. This is the corresponding set of linear equations that we get from this matrix vector equation. And you can see that only one of these equations is necessary. The other one is just contains the exact same information, but written in a different form. So I'll say A1 is equal to 2A2, just picking the first one. And now I can pick A2 to be arbitrary. I'll just choose 1, convenient. I get this as an eigenvector for the eigenvalue R. So I get two solutions to this system of differential equations. I'll call the first one x1 of t is equal to 1, 2, e to the minus 1 times t, so minus t. And the second solution I get, call it x2, is 2, 1 times e to the 2t. And we can check these and make sure that these are correct. If we plug this in, we get 3, 2, negative 2, negative 2 times 1, 2, e to the minus t. So this gives us 3 minus 4, that's negative 1, and 2 minus 4, that's negative 2, e to the minus t, and this is 1, 2, e to the minus t times negative 1, which is the derivative of x1. And we can similarly check the other one to see that it satisfies this system of differential equations. Okay. Now I want to expand a little bit on this. First of all, I'm going to write out the general solution. So it's just going to be a linear combination of these two solutions. I'll write as C1, 1, 2, e to the minus t, plus C2, 2, 1, e to the 2t. And what we have from the existence and uniqueness theorem is that we should be able to get a specific solution regardless of what our initial conditions So we might have as an initial condition is x of 0 is equal to 1, 2, for example. Or let's maybe do something more interesting. Negative 2, 3. The procedure for solving these will be the same no matter what. Now we can take this 0 and plug it into our general solution here. What we get is x of 0 is equal to C1, 1, 2, plus C2, 2, 1. And what you might notice is that this expression right here can be rewritten as a matrix vector multiplication. It'll make it a little easier to see what we're trying to do here. This is 1, 2, 2, 1 times the vector C1, C2 equals negative 2, 3. And now what we can do is just solve this matrix vector equation. There are lots of different ways to do this. We could multiply that out and get the corresponding system of linear equations and solve that using any of the old methods for solving systems of linear equations that we had before. We could, if you're familiar with Gaussian elimination, we could form the augmented matrix just as a preview for those of you who haven't taken 321 yet, or 322. We form this augmented matrix, and then we do a process of taking multiples of rows and adding them to other rows in order to eliminate certain elements. So we get a simpler system of equations. Essentially, the same thing we would do if we multiplied this out and got the system of linear equations and solved it using one of the old methods. But now just written in the form of a matrix. Another possibility is that we could just take this matrix and invert it. We have a formula for the inverse of this matrix. So it's, well, we swap the things on the diagonal. There's nothing to swap. Swap 1 and 1, looks exactly the same. And then we take the negative of the off-diagonal entries, and we divide by the determinant. So the determinant will be 1 minus 4. That's negative 3. So negative 1/3 times this matrix. This is the inverse. So if we multiply this on both sides, what we get is I times C1, C2, which is just the vector C1, C2, equals, now we multiply on the right-hand side, negative 1/3, 1 minus 2, minus 2, 1, negative 2, 3. And so what do we get for this? I'll do the multiplication by the fraction at the end. I get negative 2 minus 6, so that should be negative 8. And negative 2 times negative 2, that's 4, plus 3, 7. And so what we get is vector negative 8/3, negative 7/3. And so now our solution, given this initial condition, x of t equals negative 8/3, 1, 2, the minus t, minus 7/3, 2, 1. And again, I'll caution you, if I've made any mistakes. I haven't worked out this problem separately. I wanted to let you have the experience of seeing someone supposed to be an expert making mistakes. It's okay to make mistakes. Okay, another example. So the matrix for this one is this. the first row is 1 minus 2. The second row is 3 minus 4 times x. And maybe, you know, if normally I were teaching this class and there were people here, I would pause now and give you a chance to work this out on your own. But through the magic of YouTube, you can just pause the video. Just pause the video right now. Give it a try. See what you can. Okay, so to those of you who paused the video, welcome back. To those of you who didn't, shame on you. Let's solve this system of equations. We'll get the eigenvalue eigenvector pairs, or the eigenpairs. You just say eigenpairs. I'll go straight to the characteristic polynomial, although there's nothing wrong with writing out every single step. In fact, when you're on the exam and you write out every single step, I'll be able to find more excuses to give you partial credit. You could even try to work out this multiplication in your head, but I don't recommend it. I don't even want to do it. Okay. So this is what we get for our characteristic polynomial. And then we just do a little bit of multiplication. R squared. Let's see, we have 4r minus 1r, 3r, and then negative 4 plus 6. So that's plus 2. And again, we have a quadratic that factors really easily. So this will be r plus 1, r plus 2. When we set this equal to 0, we get that r is either negative 1, negative 2. So for the r equals negative 1 eigenvalue, we'll have the matrix 1 minus negative 1, that's 2, minus 2. And now I'm expecting this to be 3, negative 3, because we know that what we found is a value of r that gives us a matrix with a 0 determinant. Now this implies that the rows of this are not linearly independent. In the case of just 2 rows, one of them has to be a constant multiple of the other. So when I take negative 4 and I subtract from it negative 1, I do in fact negative 3. So maybe I did a little bit more arithmetic writing this matrix out than was necessary, but it's at least helpful to confirm that probably this eigenvalue is correct. Less likely that I've made a mistake. So we have 2a1 minus 2a2 is equal to 0. Of course, that just means a1 is equal to a2. And we can choose any arbitrary value for a1, and a2 will be the same thing. This is our eigenpair. Now for r equals negative 2, I get 3 minus 2, 3, negative 4, minus negative 2, negative 2. In this case, it's very obvious that these things are not linearly independent. They are, in fact, dependent. What I get is 3a1 minus 2a2 is equal to 0. I'll just go ahead and add the 2a2 over the other side. And now a little trick. I'll say that a1 is 2 and a2 is equal to 3. And that makes it kind of, you know, an easy way to make these things each other. Just make them both 6. Make both sides 6. Okay. So now we have this eigenpair, and we can go ahead and write up our general solution. So the general solution will be x of t is equal to c1, 1, 1, e to the minus t, plus c2 times 2, 3, e to the minus 2. Now let's impose an initial condition here. And that initial condition, I'm always going to put this initial condition at 0 just because it'll be easier to work out the math is. But it's not so hard to do it for an initial condition, not at t is equal to 0. But anyway, let's do x of 0 is equal to -1, -1. We can pick any initial condition at random. And the book does have some examples with initial conditions. So you can try those out. These are actually coming from the book. So it's easy to just come up with examples on your own too. As long as we end up with a matrix here that has distinct real eigenvalues. The other cases will come to you soon. Okay, so just to show what we're trying to do, this is the matrix vector equation that we get whenever we plug in 0, and we rewrite this C1 times 1, 1 plus C2 times 2, 3 as a matrix vector equation. I'll do the inverse again. What's the determinant of this matrix? It's 3 minus 2, that's 1. So dividing by 1, I don't have to do anything. And so I get, if I call this thing A, that A inverse is equal to 3 minus 2 minus 1, 1. And if I want to get C1, C2, this is just going to be 3 minus 2 minus 1, 1 times minus 1 minus 1. What do I get for this? I get -3 plus 2, -1, and then I get 1 minus 1, 0. In fact, in this one, what we get is that our specific solution is going to be -1 times 1, 1. I'll just write it as -1, 1, e to the minus. Barring the possibility that, the very real possibility that I've made some mistakes. Now I'm going to take a little bit of a detour. I think on the final exam, at least on the web work, you're never going to do deal with any matrices that are bigger than 2 by 2. But this technique extends in a completely straightforward way to matrices that are 3 by 3. Let's do one of those. This would be a system of 3 linear first order homogeneous ODEs with 3 functions. What's an example of this? X prime is equal to 1, 1, 2, 1, 2, 1, 2, 1, 1, X. And again, we know how to solve these. We've seen examples for 2 by 2. Again, we're doing the exact same thing. We're finding the eigenvector eigenvalue pairs. There'll be 3 of them in this case. We're assuming that this has 3 distinct eigenvalues, 3 distinct real eigenvalues. And we know exactly how to proceed from there. Now, how do we get the eigenvalue eigenvector pairs? We form the characteristic polynomial, which is the determinant of, if I call this A minus Ri. So just subtracting R from the diagonal entries, computing the determinant. And you know how to compute the determinant of a 3 by 3 matrix because you've done this in Calc 3. So maybe pause right here and give this a shot, see what you come up with. So what do I come up with? That's the question. The determinant of 1 minus r, 1, 2, 1, 2 minus r, 1, giving myself a lot of room. And how can I compute the determinant of this? Now, the way that you computed the determinant in Calc 3 was that you went across the top row and for each of these entries, you looked at the submatrix that you got by eliminating that entry's row and column. What we're left with here is this submatrix. So what we're going to get is this thing times the determinant of this thing. And now, of course, we know what the determinant is for a 2 by 2 matrix. So what we're going to get is 1 minus r times 2 minus r times 1 minus r minus 1. Right? These entries, subtract the product of these entries, and then subtract the product of these entries. Now we do the same thing going across this top row, but keeping in mind that we have to respect this alternating sign. So the alternating sign rule is going to go plus, minus, plus. So the next one is going to be minus 1 times the determinant of the submatrix that we get. I need to switch to another color here and here. So that's what we get when we knock out that row and column. We get that submatrix. So it's going to be 1 times that determinant. And that determinant is 1 times 1 minus r. Switch back to black. Minus 2 times 1. So that's going to be what we get for this entry in the top row. And then plus 2 times the next submatrix, which is going to be this one. 1 minus 2 times 2 minus r. Now we just have to do the multiplication, collect like terms, and we have our polynomial. Now in this case, we should get a cubic characteristic polynomial. And we'll see if we can get roots to this thing. So what do we get? At the top here, I'm going to have 1 minus r times r squared. We got minus 1r minus 2r, so that's minus 3r. And then we have 2 minus 1, so that's 1. And then minus 1 plus r plus 2 plus 2. And then maybe I'll do all of this multiplication in one step. So that's 2 times negative 2, that's negative 4, negative 8. And then 2 times negative 2, that's negative 4 times negative r, so plus 4r. So I'm going to get r squared minus 3r plus, actually, let me do this in a way that's a little bit neater. R squared minus 3r plus 1, and then the negative r is going to give me negative r cubed plus 3r squared minus r. And then we get a plus 1 from here and a plus r from here, so I'll just wipe that out. and then a minus 6, and a plus 4r. And now it's a little easier for me to collect all these terms together. And I get minus r cubed plus 4r squared plus r minus 4. And the form of this makes it a little bit easier for us to figure out what the factorization of this thing is. We see if we take these two terms and these two terms, and we group them together, then we can factor out r squared here, negative r squared. We get r minus 4 plus 1 times r minus 4. And so what we get is this is equal to r minus 4 times 1 minus r squared. Right? And then from this, we can get the roots. So the roots are going to be 4, 1, negative 1. Okay. Now let's find the corresponding eigenvectors. You might have to consult your notes to see what the matrix was. I'm going to. Let's see. Let's start with r is equal to 4. So the matrix that we get, A minus Ri, this will be equal to 1 minus 4, that's negative 3, 1, and then, sorry, 3, negative 3, 1, 2, 1, 2 minus 4, that's negative 2, 1, 2, 1, negative 3. And we're looking for an A1, A2, A3 that gives us 0, 0, 0. Now, in this case, it's not so easy to see that these rows are, they're not linearly independent. We can take a linear combination of two of these rows to get the other one. Now, I'll show you that this is in fact the case, even though we know that it should be. So if we add these two rows together, what we get is minus 2, minus 1, 3. And you see that this row is just the negative of this row. So if we took negative 1 times the first row plus negative 1 times the second row, then we would get the third row. Okay. So that shows that they're linearly dependent, right? The first two rows are linearly independent. One is not a multiple of the other, but the third row can be written as a linear combination of the first two rows. So the first two rows contain all of the information that we need from the whole system. So maybe that'll simplify the work that we have to do a little bit. Anyway, how can we solve this? Well, one way is just to do the old technique of multiplying this out. Negative 3a1 plus a2 plus 2a3 equal to 0. a1 minus 2a2 plus a3 is equal to 0. And then just solve this using any of the old techniques that we had. So what I'm going to do is I'm going to eliminate the a3 first. So I'm going to multiply the second one by negative 2, and I'll get negative 2a1 plus 4a2 minus 2a3 is equal to 0. And then I'll add the first and the third one to get minus 5a1 plus 5a2 is equal to 0. And this allows us to say that a1 is equal to a2 just by doing a little bit of algebra there. Now we can take this fact and plug it into any of these equations, and except this one. That's the one that we use to get this. So any of these other equations that we have, let's say this one, we'll plug this fact into this one to get a1 minus 2a1 plus a3 is equal to 0. And working out a little arithmetic, we get a1 is equal to a3. And so we have a1, a2, and a3 are all the same. And so for this one, we get an eigenvector of 1, 1, 1. And we have one solution to this equation. x1 of t is equal to 1, 1, 1 e to the 4t. Now let's try r is equal to 1. I think we have time to finish this problem. R is equal to 1. So the matrix that we get for this, A minus Ri, will be 0, 1, 2, 1, 1, 1, 2, 1, 0. Can you see a linear combination of these two that gives you the first two that gives you the third one? Well, it might be a little easier to see a linear combination of the first and the third one that give you the second one. So if you add those two together, you get 2, 2, 2. And of course, that's 2 times 1, 1, 1. And so 1/2 times the first one plus 1/2 times the third one will give you the second one. Anyway, what I'm going to do is expand this out and get the system of equations. A2 plus 2A3 is equal to 0. And A1 plus A2 plus A3 is equal to 0. And then I'm going to subtract the first one from the second one to get A1 minus A3 is equal to 0. And I get A1 is equal to A3. And then let's substitute this fact into the second one. That will give me that 2A1 plus A2 is equal to 0. Or A2 is equal to negative 2 times A1. And so we'll choose A1 to just be 1. And what we'll get is 1 and 1 for A3, and then negative 2 for A2. So we get a second solution, x2 of t, 1 minus 2, 1, e to the t. Now the final one is r is equal to negative 1. And so for this, we get the matrix A minus Ri is equal to 2, 1, myself a little more space, 2, 1, 2, 1, 3, 1, 2, 1, 2. And now we can see definitely that these are not 2, 1, 2, and 2, 1, 2 are the same. So the system of equations we'll try to solve is 2A1 plus A2 plus 2A3 and A1 plus 3A2 plus A3 are both equal to 0. And I'll take, let's see, I'll subtract 2 times the second one from the first negative 2a1 minus 6a2 minus 2a3. I'm going to add this one. What do I get? Negative 5a2 is equal to 0. We get a2 is equal to 0. And plugging that into the first one, for example, I get a1 is equal to negative a3. And so I can get for an eigenvector for this 1, 0, minus 1. My third solution, the x3 of t is 1, 0, minus 1. And minus. Of course, as I've said multiple times, there's always the possibility that I've made a mistake in working these out, like anybody else. So check it against yours. Also, we could take this up to the original equation here, plug it in, see if it satisfies the equation. We could check that for all three of these if we want to confirm it even further. Now, what would I do if I wanted to get the initial value problem version of this? I wanted to solve this for some initial conditions. Well, let's just come up with some initial conditions. Let's say x of 0 is equal to 1, 1, 1. Make it easy on ourselves. Well, then the matrix vector equation that we're going to end up with is 1, 1, 1, 1 minus 2, 1, 1, 0 minus 1 times C1, C2, C3. Equal to 1, 1, 1. And we would have to solve this system of equations. Let's see, what can we do? Well, let's solve it the old way by expanding this out to a system of equations. C1 plus C2 plus C3 is equal to 1. C1 minus 2C2 is equal to 1. C1 plus C2 minus C3 is equal to 1. Okay, now I can add the first and third one together to get 2C1. I guess it doesn't matter. 2C1 plus 2C2 is equal to 2. I can add it to the second one to get 3C1 is equal to 3. And already we have C1 is equal to 1. Now, plugging this in, I get 1 minus 2C2 is equal to 1, or C2 is equal to 0. And finally, 1 minus C3 is equal to 1. And this gives me C3 is also equal to 0. So in this case, we would have x of t. The specific solution for this initial condition right here is 1, 1, 1, e to the, that 4? Yeah. 1, 1, 1, e to the 4. When we plug in 0, we see that we do in fact get 1, 1, 1. And if we plug this into our initial, our original ODE, we'll see that we get the derivative of this. Okay. So there's about 5 minutes of time left. Is there anything that I want to try to fit in that? basically it. This is really everything that I wanted to fit in. So I'll go ahead and end this for today. Tomorrow, I'm going to talk about complex eigenvalues and how we deal with those. You'll see it's very similar to how we dealt with complex roots of the characteristic polynomial in the second order ODEs. We'll have oscillatory solutions. And then on Monday, I'm going to try to cover what happens when we have repeated roots. Repeated roots of the characteristic polynomial. It's a very similar situation. And then on Tuesday, we'll have a review day where we'll just do practice problems. And then Wednesday will be the exam. Now I'm going to have the exam open Monday, Tuesday, and Wednesday. If Wednesday is not a good day for you and you want to do it early, it'll be open for 3 days. The final exam will cover just the topics from that we've covered since exam 3. So series solutions and systems of first order linear ODEs, homogeneous. We're not going to get to the non-homogeneous case. We're just not going to have time. Now, I will say that the homework does not cover the situation of complex eigenvalues or repeated eigenvalues. So at least the complex eigenvalues part will be on the exam. So just a heads up. Okay. As always, if you have any questions, you can email me, or you can come to class tomorrow. And if you're watching this today, and I'll have office hours after class tomorrow as well. So on that note, you have a good day.